This talk will be more storytelling. You will not find too many formulas here. When I'm saying storytelling, it's almost like a fairy tale. So I'll start with first giving acknowledgements. The project, the daily project, was a very, very good collaboration with Norsk Grensekontroll. It's also very good to see that many of the contributors are listening in on this presentation. So that's good to see. So we had a very good contribution, a major contribution from Lina and her amazing colleagues. And without them, we wouldn't have had success. But we have also, during these 4.5 years, established a group within Equinor, securing great development and a solid implementation. I also want to acknowledge my colleagues, which have given contributions to this presentation as well. So, giving my background, I have a master in physics, geophysics from NTH, which is NTNU now these days. As you can see, my first batch to the left, I started working in Hydro back in the pre-Cambrian days. I started in the exploration, moved over to production, then computer science, and the latest, or the last 20+ years, I've been working with virtual reality visualization, natural language processing, and machine learning, deep learning. When my sons got hold of this image of the badge, they said that, Dad, you're actually a model for a Napoleon the Dynamite. And I actually have to admit that there are some resemblance, but apart from that, I think I'll just stick to my own profession. But actually, on my private side, I have an interest of enjoying use of song and humor with my yearly Christmas videos. So most of them can actually be found on YouTube. So if you have some interest, please not during while I'm presenting, but afterwards, you're I would just find it amusing if you go in and search for Hadde Jula on there. Actually, there's been 160,000 views on these. But let's get serious. So my talk is parted into 4. I'm gonna first just give some slides about Equinor and our effort within digitalization. Then, since many of you, I guess, seismic is a bit unfamiliar, I'll give some background of what seismic is, because seismic is also the backbone of the daily project. And then, of course, I'm going to be talking about the daily project. And at the end, I definitely want to show you some of the great results that we've achieved with the daily. So, as Lina stated, and as you can see from the logo, I work in Equinor. And just last week, we had a thoroughgoing reorganization of the whole company. So we moved into a matrix organization, and research is now organized in the business area, technology, digital, and innovation. This business area has the important task to improve safety, increase value creation, reduce emissions, and develop low carbon solutions. So fundamental changes are happening in the energy business, and faster than ever before. So what we are saying with this slide is that we are an energy company committed to long-term value creation in a low carbon future. We are engaged in more than 30 countries, or actually, I think it's actually 30 countries now, with more than 20,000 employees. Our revenue, as you can see to the left, is quite good. In Q4 last year, we made earnings of almost $4 billion. And oil and gas is, of course, a huge importance for the company. But as you can see, our investment in new energy is already supplying 1 million homes. Digital is one of the key words in the business area where research belongs to. And we've been working with digitalization of Equinor for several years and have made strong commitments. All data, all analytics are, and also I would say microservices are connected into the Omnia platform, which is our data platform. And we are in the process of moving everything of this into the cloud. As you can see, we are relying on the Microsoft Azure. And I won't say that we're there at the moment, but in some years' time, we will have completed the step into a complete digital workday. So seismic, I'll giving you the why, what, and how. And I'm gonna have some figures here. So let me start at the bottom right. This diagram is showing the geologic principle for an oil field. And at the bottom here, you see what I've called a source rock. And that typically is a rich shale when buried reaches the correct temperature for hydrocarbon expulsion. And the gas and the oil finds its way slowly towards the ocean bottom. But if we're lucky, the hydrocarbons hit a reservoir rock, a porous rock, and stays in this porous rock if it has a good seed rock above. So that is, I would say, the necessary underlying for having an oil field. Now, if you take a look at the left, I'm giving you an image of how seismic is being collected. So we typically have a vessel shooting sound waves down into the ground. And every time we have a change in the acoustic impedance, some of that energy is reflected upwards. Rest of it continues down, and the further down it gets, the weaker the signal gets, the frequency content drops, and also the resolution decreases. So why seismic? Well, as you can see from my text here, one single well is in a typical cost between 30 and 100 million US dollars. And if you had like this field down to the right, to manage to actually extract the necessary information of the extension of the field, where it's oil, where it's gas, and so on, would take quite many wells. So with seismic, which is a lot more cheaper, you're able to get that initial information, which is quite important. And to collect that information, you typically have a vessel, as you can see from the upper right, a seismic vessel collecting this. To do this, you need some very, very long streamers to collect these weak signals, which are reflected from the subsurface. This is an illustration showing how long they are. If you place one of these vessels in the harbor of Oslo, the cables would go all the way up to Holmenkollen. But the result is that you get a 3D seismic cube condensed with information. Luckily, we've seen some huge improvements in seismic over the past decades. We've moved from 2D to 3D seismic. We've seen improvements in the way of gathering and processing with wide azimuth, multi-azimuth, and full azimuth seismic. We also now have techniques where we place the receivers at the ocean bottom. We also use that technique to do permanent reservoir monitoring so that we actually on specific fields, like Grane field, have these cables constantly down there, and every half year can do a survey so that we're able to detect where or the movement of the gas and the fluid. We have improvements in the cable and sensor technology and also the sensor sources. And of course, we've seen huge improvements the past decades on the processing algorithms and the computing power. So you could say that with increasing or in the improvements in the acquisition technology, we've also seen a great improvements in the seismic resolution. And that means that we're actually able to detect smaller and smaller reservoirs. And also understanding the geology a lot better. So 3D seismic data is, I would say, the key to unlock the understanding of the subsurface. And I'll give you an example from Brazil offshore, and we'll take a look at one of these seismic slices here. This survey that we're going to be looking at is typically 4,000 square kilometers, and that is actually also a typical size for a survey outside on the Norwegian continental shelf. So here's the seismic profile from offshore Brazil in the Santos Basin. We have a, let's say, a scale, a time scale here on the right for that exact position. So as you can see, we're reaching down to almost 150 million years back in time. And this, I would say, the time between 65 and 150 million years back in time is quite interesting, because that was when we had the great breakup of all the continents. And Africa and South America was at that stage drifting apart and creating basins which were filled in. If we take a look at one of these, let's say, events, seismic reflections, which represents then, let's roughly 130 million years back in time, we can actually interpret this with an automatic way. So that means that you're able to, let's say, select a reflection, you enter a seed point, and the technology takes care of it. The auto tracker finds the most obvious corresponding point on the neighboring seismic traces. So you could say it's growing, the surface grows out until maybe it hits something it's not able to find correlating information on the next trace. For instance, if you have a fault. If the auto tracker doesn't succeed, then you're actually forced to do manual interpretation, which is, of course, a lot more time consuming. But let's enjoy this case here where we've had automatic tracked surface. And on this surface, we now have an attribute. It's the seismic amplitude that we've displayed on this surface. And we take a look at the whole surface. We actually get a fantastic view of this image, let's say the geology, 130 million years back in time. What we see is actually a source to sink image. On the left side, we have the onshore, and then we actually have the parallel beaches, where actually represents a sorting mechanism of the sediments coming from the onshore. And so the sediments are then transported because of the current. Actually, here you see some beautiful incised features transporting the sediments further out in the basin. And then we have a final storage out here to the right. So we often say that the presence is the key to the past. So modern events don't differ from the past. And that's why it's important for geologists to travel and observe geology and study outcrops. And we know for a fact that currents cause mass transport, just like these longshore drifts. So these actually took these sediments and caused these canyons, and then made a very beautiful submarine fan, which here is a good reservoir. But remember, we would also need a good source, and we would need a good seal if this would actually be a possible prospect. So great example, but geology can be a lot more complex. And that is because we often have faults. We have quite complex geology with these faults. We have salt tectonics, which could really shake or stir around the geology. We have volcanic events with the silts and dikes, which causes very strong reflections and disturb the seismic. We have intrusions and movements of sediments. We have amplitude anomalies and erosive processes and phases changes. So all of this could actually force the interpreter to move from doing automatic interpretation to manual interpretation. And then we have the seismic acquisition and the processing, which also has its challenges to cope with noise, diffractions, multiples, attenuation, resolution, sampling rate versus aliasing, frequency and content, anisotropy, acoustic versus elastic waves, and the list goes on and on. And when we're talking about resolution, this is an example from Chaloffy in France, a great outcrop where we have trips to. And we could actually go even closer, but you see a lot of detail here. All of these packages of sediments. I'm pointing here, this is typically a 25, 30 meter package of great sand rocks. Here we have another package. But what if we took this, buried it down to 1.5, let's say 1.8 kilometers? How would the seismic be able to give that information? Well, actually, it would be quite coarse. It would be very difficult to understand all what is in between these layers. So that is one of the reasons why also drilling is necessary to get out the detailed information. So let's move on to the deep learning part of this talk, and I want to go in and say, give you the results from the daily project, how we started on and so on. But before that, let me just give you the motivation for why we started the project. So based on what had happened, let's say 6-7 years back in time, we saw that there were achievements within many areas. And of course, the question was, could we apply some of this technology on our industry within seismic interpretation? So when we looked at how deep learning made successful classifications, we could, of course, be motivated. But when that information was a bit subtle, then we saw that deep learning actually wasn't able to retrieve the right answer. So at the start of the project, our question was, how subtle is the seismic information? Are we actually able to apply deep learning on this? And of course, then we had what to target. Because within seismic, there's a lot of different information which the interpreter is trying to extract. You, for instance, have the large fault systems. You have, let's say, the minor fault information. You have, as I mentioned, the key horizons, and you also have the direct hydrocarbon indicators as this flat spot. Actually, what I'm showing here is one of the largest money machines we have in Norway. It's the Troll field, and it's been producing for 25 years. And today, during today, it will have given 27 million US. So it just gives an idea of how much money this field represents still after 25 years of production. So the question was what to target. In addition to what I've mentioned, we also have the stratigraphic elements. We have the phases as gas gyms and salt and so on. And we also have geomorphology, which is, let's say, specific geobodies that we detect in the seismic. So we were maybe a bit bold in the start of the project. We looked at 4 of these categories, but we conclude together with Norsk Central that we should actually just focus on the key horizons. Now, this was actually quite, I would say, high-hanging fruit. Most competitors, and I would say vendors, were looking at faults. And today we actually see great results achieved applying deep learning on seismic faults. But we wanted to try something different since the rest of the industry was looking at faults, so we went for horizons. Now, seismic horizon interpretation is a bit different in the company as well. You have exploration, which their goal is to understand the region. They need to generate the prospects. So detailed services is not always needed. And for the key horizon interpretation, they use the auto tracker to track the easy continuous reflections, and then they have to use manual interpretation to do the complex or subtle reflections. But then you have production. Yeah, you found the field, and you need to produce it in the most optimal way. So then you need to understand it. You need to focus on the reservoir, and details are needed. So you mainly do manual interpretation, but you could use the auto tracker now and then as well. Our project was linked to the exploration and how they were working. But it is our goal now to also cover production's needs. I just want to mention this. I liked it very much when I saw Adam Grant's TED Talk, and it showed the timeline for a creative process in the project, because it was actually very nicely described how the daily project together with the Norsk Central evolved. And in the start, we used synthetic data, and we saw that actually this is awesome. We had some very positive results. But when trying it out on real seismic, we didn't get that good results. Actually, it was disappointing. So we knew that this was going to be a bit more tricky than we thought. And when we started to develop things, actually, we were starting to question the technology. We were even starting to question ourselves. But then we managed to get a breakthrough. And we then were very positive. This might actually be okay. And after 4 years, we have proven that this is very awesome. We've managed to implement this in the company. And this is now in daily use and is regarded as one of, let's say, research's successes the last year. Norsk Central did a thorough work in investigating what detection networks and segmentation networks that would give the best opportunities. They also looked into 2D as well as 3D networks, but we ended up with as many others in the industry that the 2D UNet is the one that gave the best results. This is a sketch of how the network we call the Horizon Net, but the whole solution is called the Daily. So we made a pre-trained network that was, of course, done in the cloud. And this is the basis for any project that wants to generate predictions based on a small amount of labels. So in the interpretation system, the user does interpretation of 4, 5, 6 lines and feed it into the pre-trained network and fine-tunes that network. It does the predictions of the whole cube, does a cleanup, and we actually also do one more run before we merge them and feed it back to the interpretation system. So big data gives a huge opportunity, but it also gives a source of big mess, I would say. When we were starting to try to find data to which we could feed in for this pre-trained network, we saw that there were actually a lot of challenges because there were you could think that a company like Equinor, with all the seismic, all the interpretation, that we would have a gold mine, but it was actually quite difficult to find or detect these surveys, these interpretation projects that could go in. We also used precision recall to quantify our results to see were we on the right track. And that leads me into the results. So I'll actually start with one of the first case studies we had. You could say that it was the reason why I want to show this one was because of its ability to detect subtle features. Now, this use case was 2 years back in time. Now, in that period, we have immensely improved the end product, but it's quite interesting to go back and take a look at this because it actually was the use case that gave us the approval for continuation in the project. So we had a subtle horizon here. Let's call it just horizon X with a turquoise stapled line. And this turquoise horizon, we also gave into the auto tracker. So we gave it, said, okay, here's the label. Please do auto tracking of this. What happened was that it jumped fairly quickly up to a more stronger event above and stayed there. So the auto tracker obviously failed. So the only option the interpreter would have here would be to do it manually. Now, the daily, or horizon net, you could say, is the pink one. It is reasonable close to the label truth, but it's not precise. So this was 2 years back in time. Actually, it should be quite interesting to go back now and see how the result would be now. But this was the result at that time. In the middle, you have the auto tracker. It stopped fairly quickly, but the results on the left from the daily showed a huge potential. So actually, one of our expert interpreters that evaluated this said that it will be helpful in any project. And please, can I start using it? Second case study was actually very valuable for us because it showed how we could develop a workflow with use of daily. And this use case, which was from outside Ireland, had focus on the Cretaceous package. We had especially focus on the BCU, base Cretaceous unconformity. And the interesting thing with the BCU is that going from north to south, it actually has a phase shift in the signal. That means the above lying sediment gives a difference, changes so that actually we have a phase shift, and that forces the interpreter to do it manually. But we used daily on this. We actually got the result from this and the other 7 key horizons in within 6 hours. We did a very quick cleaning and infill interpretation. We made the interpreted surface of that, and we compared it with the manual interpretation. And actually, the manual interpretation, they used a whole week. We used 6 hours from start to end. And if you take a look at, it's not only the efficiency gain, but we also had a huge quality gain with using this. We also saw that in 2019, we managed to get a huge, let's say, improvement in the horizon net by including 2 new methods applied to. So this was the result that we had from the basement early 2019, and that was just useless. And at late 2019, actually, the daily had improved so much that we actually could use this as well. Case study number 3 is, I would say, leaving the hard work to the machine, because then we start to look upon really large surveys. And I mentioned that 4,000 square kilometers is a typical survey, but that is regarded as a large survey. Now, this is what we call a giga survey. It's 15,000 square kilometers, and it is it's huge. So it takes a lot of time to interpret this. We used actually only 4 inlines as labels, and we predicted the top salt, the base salt, the basement, and the response from the asset team was very positive, as you can see from below here. The 4th case study is, I would say, is mapping the unmappable horizons. That's this is the last case I will show you, but it's one quite recent. So it is again taking a look at the seismic, and this is from the North Sea. So there is an event here. If you see it very, it's a bit subtle probably, but I'm pointing at it here. It is a white stapled line in this blue signal. And the problem with the top Svarte is that it's quite wide. And the problem is that the peak of this tends to change position, which means that if you try to auto track this, you get a very disturbed surface. It's not that surface which you would expect, because the expectations are a very soft and, I would say, a regular surface. Now, there is one technique that you could use, and that is using the zero crossing instead. Now, it improves the image, but still the interpreter wasn't satisfied. But when we gave the interpreter the daily solution, and he himself did the predictions, he came back and said that, wow, this is really great. It's giving me exactly what I want, because it's mimicking exactly what I gave in as labels. Another example is top Oligocene, which is, I would say, heavily polygonal faulted. and it's very difficult to auto track. Again, it's the line is probably very subtle, but you see it going up and down here. I'm pointing at it here. So if you try to auto track this, it would very quickly jump just above, because you see some strong signals, blue signals, which is peaks just above. And but giving this to daily, it gives an extremely good result, because it's able to stay down at these more weaker peaks than being tempted to jump up on the stronger peaks. Of course, it's not perfect. I would say we do see some spikes here in the background, but all in all, it's probably around 95, 98% successful. And I would also want to point out that this image here would actually be impossible to present if it weren't for daily, because since the auto tracker failed, manual interpretation of this would take way too much time. So this, in summary, we've seen that the implementation of daily has given great efficiency and quality gain. It works on subtle horizons, it works on polarity changes, works on different geography, changing geology, and actually we've also developed it so it is can be applied on 2D seismic as well. Some of the interesting things that have been done lately is actually that they use the daily results to see where it's not giving as good results. And that brings attention to where actually they should focus on with manual labor. And we've also used to qualify various different seismic surveys. So if you ask me, what about the future? I would say that future development should include domain knowledge, and it should include additional data attributes. And taking a look at below, you could say that we found a very good position for Horizon and daily in the area of let's say, subtle information in the seismic image, where the auto tracker fails and where we would want to avoid manual interpretation. And our goal is to push this barrier towards the right, so that we are able to relieve the interpreter for work of interpretation, so that they can focus more time or invest more time on what creates even more value. Yep, I think I'll just leave it there. I could maybe just mention this last couple of slides. We actually did an exercise, former colleague of mine, John Thurman, and I. We looked at the levels of autonomous vehicles, how self-driving cars were categorized. And then we said that, okay, why not try to develop something similar? So we actually wrote a similar way of categorizing how deep learning can be applied to seismic interpretation, and what would be qualifying the success of each of these, let's say, results. So with that, I will just say thank you